As a kid, I always wanted to become a theoretical physicist and discover some new fundamental law of nature. And that turned out to be a bit harder than I imagined. I turned to computer science, and now I'm very much fascinated and excited by the prospect of contributing on the algorithmic side to make new scientific discoveries possible in biology, in health, or even in chemistry. I'm Niki Kilbertus. I'm a professor at the Technical University of Munich at the School for Computation, Information and Technology, and I'm also a PI at the Helmholtz Center in Munich and part of the Munich Center for Machine Learning. Artificial intelligence is really amazing at capturing associations and patterns in data. And that allows for amazing predictions in many situations. However, one aspect that these models often miss is the notion of causation. So they can't really tell which aspect or which action caused another one. They only see the association. So when we think of a medical setting, imagine there's two treatments, A and B, for, in this case, let's say kidney stones. So there's an invasive treatment A, where you have to cut open the patient and physically extract the stones, and a non-invasive treatment B that is trying to break down the stone so it can be naturally extracted. Then usually we're interested in how well these two treatments perform. Is one better than the other? Is one more effective than the other? And the outcome here of interest could be something like, is the patient pain-free after 5 days post-procedure? However, the issue here is that the treatment and the outcome are not only related via this direct effect. There may be other things that we can draw up here. For example, the patient history, right? Has this patient had previous issues with kidney stones? But also aspects like, was it a large or a small stone? And these aspects will typically inform the treatment that is being assigned. So doctors may choose to apply the invasive treatment more often when you have a very large stone that is not even feasible to be removed with the non-invasive one. At the same time, these aspects have an effect on the outcome, whether the patient is going to be pain-free. It seems natural that a patient with a very large kidney stone will take longer to recover to be pain-free than one with a small stone. So ultimately, when it seems that treatment B led to recovery more swiftly, this may be simply due to the fact that the non-invasive treatment is always assigned to patients with small stones who are going to be pain-free anyway. So to measure the actual effect of the treatment, what we would do in a clinical setting is to try to randomize it. Right? When we want to approve a new drug, we perform a randomized controlled trial, and in this case, it would amount to flipping a coin which treatment is being assigned. So instead of just taking the natural assignment, we try to remove the influences from other factors. And when we literally flip a coin for each patient which treatment is being assigned, then we can ultimately see which treatment is more effective. This is the causal effect, the actual effect of the treatment on the outcome, where you get rid of all of these unobserved confounders that may still be in the game. Instead of only discovering the patterns that already exist in the data, causal inference allows you to predict what is going to happen under future interventions. But a key component is also to take the data we have collected until this point and make predictions, decide which experiments are going to be most informative in the future. And our methods and algorithms are closing precisely this gap.